To reach these velocities, a missile must generate continuous thrust to overcome the massive atmospheric resistance that would otherwise slow it down or tear it apart. This propulsion is what transforms a static payload into a high-speed guided weapon, enabling it to maintain precision even while operating under extreme physical loads. This graphic displays the primary launch environments militaries utilize to project power. Platforms range from ground-based units and fighter jets to submarines and orbital interceptors. Terrestrial systems operate in dense atmosphere, while space-based platforms function in a vacuum. Yet, regardless of whether a missile is a short-range interceptor or an intercontinental deterrent, its performance is governed by the same set of chemical and mechanical limitations. Strip away the airframe and guidance sensors, and you find the bulk of the internal volume is dedicated to the fuel and machinery generating thrust. This architecture is the primary factor dictating a missile's ultimate strategic utility. Designers must navigate a constant engineering trade-off: the need for a weapon that can sit dormant for years but ignite instantly, versus the need for a system that can actively adjust its speed and trajectory mid-flight. This trade space is occupied by three primary architectures: solid, liquid, and hybrid propulsion systems. Analyzing these specific physical trade-offs explains the logic behind global missile deployment and why certain engines are chosen for specific geopolitical missions. All missile propulsion relies on Newton's third law. By expelling high-velocity exhaust gases downward, the engine generates a reaction force that drives the missile forward along its intended path. This cross-section shows the solid rocket motor, the most utilized system in modern arsenals, due to extreme mechanical simplicity. The fuel and oxidizer are pre-mixed into a single, rigid propellant grain. Being a solid block, it requires no moving parts to fail during ignition. This makes the system incredibly stable. Solid propellants can be stored in a warehouse or a silo for decades without the chemical components degrading. This stability makes SRMs the standard for nuclear deterrence. They allow missiles to remain on high alert for years while ensuring launch in seconds. The drawback is a total lack of control. Once ignited, the engine cannot be throttled or shut down. It burns until the fuel is exhausted. To compensate for this, engineers look at the hollow center of the propellant, a feature known as grain geometry. This specific shape is the only tool engineers have to control the missile's behavior after launch. The amount of thrust generated is directly proportional to the surface area of the burning fuel. By casting the fuel into complex shapes, like a star or a finocell, designers pre-calculate how that surface area changes as it burns, effectively programming the thrust profile into the physical fuel itself. In a solid motor, the entire flight performance is hard-coded into the geometry of the propellant before the missile ever leaves the factory. If solid motors are defined by their preset rigidity, liquid propulsion systems are designed for maximum in-flight adaptability.
In this architecture, the fuel and oxidizer are stored separately. They only meet when they are injected into the combustion chamber. This requires a complex delivery system, using high-pressure gas or high-speed turbopumps to force the liquids into the chamber at precise rates. This mechanical complexity provides a major tactical benefit. By adjusting the valves, the missile can actively throttle its thrust, allowing it to change speed, shut down, or even restart its engine mid-trajectory. These systems are also measured by specific impulse, a metric of efficiency that determines how much thrust is generated for every pound of propellant consumed. Liquid engines generally offer higher specific impulse than solid motors, making them the superior choice for long-range missions that require high fuel efficiency. But this efficiency is expensive. The network of pumps and valves increases the statistical likelihood of a mechanical failure. Furthermore, the chemicals used are highly corrosive or cryogenic, meaning they cannot be stored inside the missile long-term and must be loaded just before launch. Liquid systems buy efficiency and control, but they trade away the instant readiness and mechanical simplicity of solid rocket motors. To find a middle ground, aerospace engineers use hybrid propulsion systems, which attempt to combine the strengths of both architectures. A hybrid engine uses a solid fuel grain, similar to an SRM, but it relies on a separate tank for a liquid or gaseous oxidizer. Combustion only occurs when the liquid oxidizer is actively sprayed over the solid fuel, giving the engine a clear on-off switch. Because the fuel and oxidizer are physically separated until ignition, the system is inherently safer to handle and remains stable during long-term storage.
Yet, unlike a pure solid motor, the hybrid system can still be throttled. By adjusting the liquid oxidizer flow, the missile can vary its thrust throughout the flight. Hybrid systems successfully bridge the gap, offering a balance of dormant readiness and active flight control. With these principles established, we see how engine choice dictates launch strategy. Solid motors are the logical choice for submerged platforms and remote silos, where weapons must remain perfectly reliable without maintenance for decades. Liquid and hybrid systems are reserved for roles that demand extreme range or the ability to perform complex, fuel-efficient maneuvers in the mid-course phase. The dynamic control provided by these throttleable engines is what allows a missile to adjust its path in real time, a mechanical requirement for the high-precision, autonomous targeting systems seen in modern conflict. This evolution is pushing toward the hypersonic regime, where engines must operate under unprecedented thermal and aerodynamic loads. While guidance software and AI continue to advance, they are ultimately limited by the physical ability of the engine to translate those commands into thrust. A missile's role is never a matter of chance. Its range, its speed, and its strategic purpose are all defined by the unyielding physics of the engine at its core.